Are you interested to design your own home security system? That can be a smoke detector, can be an anti-theft alarm, or something else that can connect a sensor with a buzzer. So if you are interested to do such kind of thing at a very low cost, then welcome to Adisha, the lecture in electronics and optics, where I will demonstrate you how to design a very low cost smoke detector or anti-theft alarm using 555 timer IC. And the particular application that I'm going to use over here, that is called the monostable multivibrator. And why it is called monostable multivibrator? You will see in this tutorial that the 555 timer has the two state. One is the plus VCC, that means the most positive supply available to the circuit, and next one is the minus VCC, which is the most negative supply available to the circuit. And for this purpose, I'm going to use the plus 8 volt for the positive supply and the ground volt for the negative supply. So the 555 timer IC has these two states, and in case of monostable multivibrator, it has only one stable state, and that is the ground state. So when nothing is happening, no trigger gets applied, then you will see that your output stays at the zero state or the ground state. And when the trigger gets applied due to some smoke presence in the room or something unlikely happening surrounding your homes, and your motion detector is detecting that unlikely motions of that, and it triggers up the device, then the output of the device switches to its quasi stable state. So that is equivalent to the plus VCC, which is the most positive supply available to the circuit, and it will ring the buzzer, and the buzzer will ring for a time duration. And your purpose for this tutorial, I will show you, and being an engineer, you have to design the time duration over which you want to make your device to stay at its quasi stable state in order to ring the buzzer. So let's start with the monostable multivibrator using 555 timer IC. So if you find this video is helpful for you, please like, share and subscribe, and please make comment on various topics if you want me to make another videos on your choices. This one represents the internal circuit diagram for the 555 timer IC, and this one on the left represents the pin diagram of the same IC, where the pin number 8 is used for the most positive supply, and that is denoted as the plus VCC. In this tutorial, I am going to use plus 8 volt as the plus VCC or the positive supply. On the other hand, the most negative supply that I will use it over here, that is the ground potential, and that is connected with the pin number 1. Pin number 5 is known as the control voltage, although not in this tutorial. In my next tutorial, where I will discuss the astable operation, I will show you the use of the pin number 5, and using this pin number 5 along with the astable operation, you can do many interesting things, and I will show you in my next tutorial. Till then, stay tuned with my lectures. Anyway, pin number 3 is considered as the output. Pin number 7 is discharge, 6 is threshold, and 2 is trigger. Now, what about these 3 pins, how they work? For that, I need to discuss this internal circuit diagram for the 555 timer IC. So here, 2 operational amplifiers are used where we can't see any feedback resistance from the output to its inverting terminal. So that means these 2 operational amplifiers are being used as the comparator. So this is the comparator 1 and this one is the comparator 2. In some books, you may find this one is denoted as the upper comparator and this one is denoted as the lower comparator. In my tutorial, I will use this comparator 1 as the upper comparator and comparator 2 as the lower comparator. Simultaneously, I will use these names. Well, now as they are the comparator, their output can switch between plus VSAT to minus VSAT. Now what is this plus VSAT? Plus VSAT means the most positive supply available to the circuit, and that is close to the VCC, and minus VSAT means the close to the most negative supply available for the circuit. The most negative supply available, that is the ground. So minus VSAT means close to ground, plus VSAT means close to VCC. Why I will call it close to VCC? Because some of the voltage may drop due to the internal circuit, so that's why it will be the close to VCC. And when the comparator output will switch to plus VSAT, that is close to VCC, the flip-flop, which is the RS flip-flop, so the inputs of this RS flip-flop, they will get the logic 1 input for each comparator output goes to the plus VCC or plus VSAT, and when the comparator output will go to the minus VSAT, which is the close to ground voltage, so then the inputs of this R and S will get the logic 0 voltage. But from the truth table of this RS flip-flop, we know that this RS flip-flop responds for the different inputs at its R input and the S input, which means when both of these inputs are getting the logic 0, which means minus VZ, no changes will take place at the output of the Q. Here the output Q I have denoted, but actually the circuit is utilizing the Q bar, which is the complement of this output Q. On the other hand, the actual output that is coming out from the circuit, that is from pin number 3, that is the inverted version of the Q bar, which means basically I'm taking out this Q out of this box. So Q bar is connected with a transistor, NPN transistor. So when Q bar goes 1, so this NPN transistor will be turned on and it will establish a path between this pin number 7 to this ground. And this capacitor, which is connected at this pin number 7, as you can see, that can discharge through this pin. So I will discuss it over here. Anyway, so when the inputs are same, 0, 0, corresponding to minus VZ, no changes. When the inputs are 1, 1, corresponding to plus VZ, no changes will take place at this Q. But when the inputs are minus VZ, plus VZ, which means S equals to 0 and R equals to 1, so that is the condition of reset condition. S stands for set, R stands for reset. So when reset pin is 1 and set pin is 0, the output Q will switch to 0 because the flip-flop is reset. And when Q will be 0, Q bar will turn on, and Q bar will be 1, and that will turn on this NPN transistor. In the next, another state, that is the S equals to 1 and R equals to 0, that is corresponding to Q equals to 1 and corresponds to Q bar is equals to 0, and that will turn off this transistor. Well, now you are going to connect it a plus VCC without, I'm not connecting this RC right now. I'm just connecting this plus VCC to this pin number 8. So when you connect a plus VCC to this pin number to the pin number 8 plus VCC, I'm assuming you are going to get 2/3 of the VCC at this particular node and 1/3 of the VCC at this particular node. And it's very easy to understand, because if you assume that VCC is like this, if you assume VCC is a battery VCC and one resistor R, another resistor R, another resistor R. So in that case, this is R, and this one is R. So this one is one node and this one is another node. So when you are going to calculate the potential at this particular node, so that includes the voltage drop across the 2 resistor of equal values out of these 3 resistor of equal values. So that means potential at this particular node will be 2R divided by 3R times VCC, and that will give you 2/3 of the VCC, and that's why it's appearing 2/3 VCC. In a similar manner, when you will consider only one resistor out of these 3, so that the 1/3 of the VCC is going to get at this particular terminal. Well, now let's see the connection for the monostable operation. Here only one external resistor that is used. However, these are and these are, they are different from each other, because these are the internal to the circuit, I mean to the IC itself, and these are is externally connected component. Generally, the values of these 3 resistors are of 5 kilo ohm, and that's why some people think that the name this 555 timer is appearing due to these 3 5 kilo ohm resistors. But I personally think that instead of this 5 kilo ohm resistance, if you apply 6 kilo ohm resistance, then also this circuit should work properly, because the purpose of the resistance is to establish this reference point at this pin number 5 and at this point. So whatever the value of the resistance, when they will be equal to each other, so the same reference potential will appear over here. So there is no big deal to use this name 555 that is regarding these 3 5 kilo ohm resistance. Anyway, pin number 2 is used for the trigger. Now generally when nothing is happening, for example, as I told, you are going to design your smoke detector and within your room there is no smoke, so your device will not, or your device should not trigger up the buzzer. So that's why the trigger must be connected with the VCC, because in order to ensure that the output will be at its stable state. As I told, the stable state is a zero state, because when the trigger will be connected with the VCC plus the plus VCC, this is the VCC, trigger must be connected with the VCC, then the inverting terminal, input at the inverting terminal of the comparator 2 will have higher potential than its non-inverting terminal, because this one is 2/3 of VCC and this one is 1/3 of VCC. So when this trigger terminal is connected with the plus VCC, so the output of this comparator 2 will be minus VCC, corresponding to logic 0 input for this S input of the hardest flip-flop. On the other hand, since this pin number 6 is connected with a capacitor which is initially discharged, no charge is holding by this capacitor, so the potential at the non-inverting terminal of the comparator 1 is also 0, whereas the potential at the inverting terminal of the comparator 1 is 2/3 of the VCC, which is higher than its potential at its inverting terminal. So that means the output of the upper comparator or the comparator 1 is also minus VCC, corresponding to the input logic 0 input for the R input also. And that is the condition that you can see over here, that both of these inputs are 0, 0. No changes. No changes means the output will stay at its stable state, that is the 0 state. Okay. Now you are going to apply the trigger. Application of the trigger is a tricky thing for this monostable application. I will show you next. So this is, you have to apply the negative edge trigger. Negative edge trigger means initially this trigger was connected with this one in order to ensure that output will stay at its 0 state. Now when you are going to apply the trigger, you must have to connect the trigger with the ground, and immediately after that you have to reconnect with the VCC so that a negative pulse gets generated. Now think about with respect to your sensor, so smoke sensor that generates a signal against the detection of the smoke if present within your room. So that signal may be continuous over time, for that signal can stay for a while, but your trigger must be a negative edge trigger. So that's why before applying the trigger, you must have to do some arrangement so that the signal that is coming from your sensor must be treated as negative edge trigger. Well, I will show you in this tutorial also how to apply the trigger. Anyway, so now I'm considering that I have applied the trigger, that means I have connected with the ground and I have reconnected with the VCC. Just keep it in your mind that I have reconnected with the VCC. So which means when I connect this trigger with the ground, at that moment of time, the potential at the inverting terminal, which is getting 1/3 of the VCC, is higher than the potential at than its inverting terminal. So the output of the comparator 2 will switch to the plus VCC, and that will set the flip-flop, because the S is going to get the logic 1 input while the R is still having the logic 0 input. So the condition S equals to 1, R equals to 0 means S equals to plus VCC and R equals to minus VCC, corresponding to Q equals to 1. But here I'm considering Q bar, so Q bar is equals to 0. Since Q bar is equals to 0, output will switch to the logic 1, or output will switch to the plus VCC, because the output is the inverted version of the Q bar. Basically, output is nothing but the Q itself. So output is 1, Q bar is 0. This transistor is turned off. When this transistor is turned off, so there is basically no path between this pin number 7, that means at this point where the capacitor is connected, through the ground. So this path is off. So the current from the VCC will flow through this resistor and through the capacitor. And you may ask why it can't flow through this comparator, because this pin number 7 is connected, because the pin number 6 is connected, which is the input terminal of the comparator at this point. Just imagine the property of the operational amplifier, where we generally assume that the input impedance for the operational amplifier are so high that literally a very negligible amount of current flows through the input terminals of the operational amplifier. So that's why we can safely ignore any current which is flowing through this pin number 6 to this operational amplifier, and the majority of the current should flow from the VCC through the R and through the capacitor, and during that time capacitor gets charged up. And when the capacitor is charging up, look at that, potential at the pin number 6 is rising. And one more thing I should mention, that the trigger I have applied and after that I have reconnected with the VCC, meaning that immediately after applying the trigger, the output of this comparator 2 again switched back to the minus VSAT, giving the 0 input for this S. And right now the capacitor voltage is increasing, and when the voltage across the capacitor is increasing, and it will just reach the 2/3 of the VCC, which is the reference voltage for this comparator 1, then the potential at the non-inverting terminal of the comparator 1 will be higher than that of the inverting terminal, and the output of the comparator 1 will switch to the plus VSAT. So what is the condition right now? Condition for R input is the plus VSAT, that means the logic 1, and for S input it is logic 0, because I have reconnected the trigger with the VCC, giving the minus VSAT input to the S. So R equals to 1 plus VSAT and S equals to minus VSAT. So R equals to plus VSAT, S equals to minus VSAT. This is the set condition corresponding to the output Q, output 0 for the Q, but Q bar is 1. When Q bar 1, output will switch back to its stable state, that is the ground state, and before that output was at the high state, and now it will come back to its stable state. But Q bar is 1. When Q bar is 1, this transistor will turn on, and when it will turn on, it will establish a path between this pin number 7 and the ground, and the capacitor will discharge immediately, because this is the smallest resistive path ever found by the capacitor during its operation. So immediately after the capacitor voltage will reach the 2/3 of the VCC at this pin number 6 terminal, the output will switch back to its stable state, that is the 0 state, and the capacitor will be discharged immediately. So that's why this operation is called the monostable, because for the time the capacitor is charging from 0 to 2/3 of the VCC, the output can stay on its quasi-stable state, and during that time if you connect a buzzer at its output, you can get a constant ring for that. Okay, and during the monostable operations, suppose for your smoke detector project, during the operation you have set the time for this capacitor to charge up to 2/3 of the VCC, say for 20 minutes, but during the time you have managed to remove all the smokes from your room, but still your buzzer will ring. Then you need to reset the device, because there is no problem anywhere. You can ensure that, and then you have to press the reset pin, and as you can see, the reset basically resets the flip-flop, and resetting the flip-flop, it resets the output. So it is the negative voltage is required, because this bubble means it's a negative edge triggered. Here also you have to give a negative voltage for that. So this is the operation of monostable multivibrator. Now I will show you through an animation how we can apply a trigger. But before applying the trigger, I must calculate the time for which I want to keep my operation, my monostable operation output at its quasi-stable state. Say for example, I am considering that for this demonstration purpose, I am considering that my output will stay for 2 milliseconds at the quasi-stable state. So let's see what type of calculations we can perform. So for that purpose, I'm going to use this software that is called Maxima. It's an open source software, and you can do many calculations with Maxima. You can solve multiple linear equations. I do love to use this software, although the calculations associated with the monostable operation is so simple that you may not need such kind of software. It's a simple calculator can be suitable for that. But in order to give you a very brief introduction of this Maxima, I'm just trying to demonstrate this one. But however, as I told, even for a very simple calculation, I do love to use this Maxima. Anyway, so generally, the equation for the time period for which the output stay at its quasi-stable state, that is counted as 1.1 time R times C, which are that external R that I have shown you through which the capacitor gets charged up. So as I am considering that for our design, I'm considering that T is going to be 2 millisecond, or that is 2e minus 3. So that is the expression I'm going to use for this maxima. And R, I should calculate the R for given values of C. I'm going to calculate the C as 0.1 microfarad. Now with these values of R, now with these values of capacitor and the time, what will be our values of R? So that is the thing I'm going to calculate. It's a very simple calculations. So let's see. So first I'm going to the equation, solve linear system. How many linear equations I need to solve? That is 1. Okay. So now I must give this expression. So what is the expression? The 1.1 times R times C. Capacitor I'm going to use 0.1 e minus 6, and that is equals to 2 e minus 3, 2 millisecond. And the variable, obviously, that is the R. So this is the result, but this result is not a convenient one. So for that, I need to convert it into the numerical one. So and that can be done using the percentage, and this percentage basically refers the immediately previous output. So basically this output is being referred through this percentage, and numar for the numerical output. Yes, look at here. So the value of the resistor is coming as 18.2 kilo ohm approximately. So these values of the resistor, 18.2 kilo ohm resistor with 0.1 microfarad of the capacitor is going to set the quasi-stable state of 2 milliseconds. So let's see using this animation. Now look at that. The value of the capacitor is set at 100 microfarad, 100 nanofarad corresponding to 0.1 microfarad, and the value of the resistor is set, this one is the resistor and this was the capacitor, and this resistor is set as 18.2 kilo ohm. So I must expect that the waveform should be of 2 milliseconds, although here I am not showing you pulse width or the quasi-stable state, the duration for the quasi-stable state, that will be seen in the LTspice platform. So here the purpose of this animation is to show you how we can apply the trigger. So when the output will go to its quasi-stable state, so this is the output line, and that will be connected with that is connected with this LED. So for this quasi-stable state, the LED will glow, and this LED is a representation of your buzzer. So I'm interested to see this output that will be of this purple color, and the voltage or the potential across this capacitor that will be of this green color. So now I'm starting the simulation. Look at it. Initially, when nothing is applied, initially this is the trigger terminal, and this trigger terminal is connected with this VCC. As you can see, this is the VCC and the positive supply, and this trigger is connected with the VCC initially. So nothing is happening, your buzzer is not ringing, LED is not glowing over here. Now I'm connecting this trigger. I have connected and reconnected with the VCC. Look at here. I just need to make it large. Look at here. So I'm applying the trigger and reconnecting with the VCC. So this is the negative edge trigger. So such connections must be done during the time the output stays at its quasi-stable state. So suppose you at some time you forgot to reconnect it with the VCC, then as you can see, the output will never switch back to its stable state, that is the zero state. Rather, the quasi-stable state will be the stable state for this particular configuration. The LED will glow continuously, your buzzer will ring for continuously for a longer period of time if you do not reconnect it with the VCC. So now I am reconnecting again with the VCC. And look, another interesting thing is that during the time when output stays at its quasi-stable state, it doesn't matter how many times you will apply the trigger. Look at here. How many times I am applying the trigger, it doesn't matter, the output states is not going to change. So look at here, I'm changing multiple number of times the trigger. Okay. So once it gets triggered, the output is not going to change. Okay. But as I told, in order to apply the trigger further, you must have to reconnect it with the VCC. Otherwise, your next circuit will not work. Okay. So this is an empty LTspice. So here I'm going to create the new schematic, going to get the NE555 IC. Now I'm going to get the battery for supply. That is going to, I'm going to use as 8 volt for that. Ground terminal. Now I have connected all the components as required. Now I need to give this trigger. For this trigger, I need to go to find for switches. Not here. It's W. These switches. So I need to I need two switches because this re-triggering, one switch will connect it with the VCC and another will connect it with the ground. So here I'm going to use this one to connect this VCC, say, and the other terminal will connect this trigger, and another terminal that will connect the ground with the trigger. So when nothing happens, so this switch gets activated for all time and connects this VCC to this trigger terminal, and when this trigger is need to be applied, this switch will be activated, turning off this one, and this trigger will connect with the ground, and immediately after that this switch will be turned off and turning on this one, so that the VCC can be reconnected with the trigger again. So for that we need another triggering signal. So that signal that is coming from say for example some device or some sensor that I told you. So here I'm simulating that device using some pulse. So I'm going to search for the voltage. So this pulse, this voltage will basically turn on these switches, these two switches, but not simultaneously one after another. Let's see how we can set this pulse. For this pulse, I'm going to set this PWL. PWL stands for this piecewise list, maybe. Okay. So here you can see the time value pair of the signals or all of the voltage. So here for time 1, what will be the value? Time 2, what will be the value? Time 3, value. Time 4, value. So these are the sets are appearing. If these are not sufficient for your operation, you can take help of this for this more data points over here. Even these are not sufficient for your data point, you can write this time value pair in an Excel sheet or in an CVS format, and you can import it through this browse button. Okay, but for our purpose this one is sufficient. So I'm considering that the pulse is going to be applied at 10 millisecond. So at 0 times 0, the value is -8. Why I am considering -8? Because basically the switch gets activated and deactivated for 8 volt, or not 8 volt, for some positive volt. So if one will be activated for that positive volt, other will be activated for some negative volt. Okay, because two switches I am considering. At time 10 millisecond, it remains at -8 volt, but at 10.01 millisecond, it switches to 8 volt to turn on, and immediately after that 10.02 millisecond, it comes back to minus 8 volt again. I hope it should work. Okay. Now, in general, this pulse voltage will stay at its minus 8 volt when nothing is happening. So therefore, the minus 8 volt generally turn on this switch 2, which connects this plus VCC to this trigger terminal. So that's why I should connect the positive terminal. So over here, I should connect this positive terminal of this V2 with the negative terminal of this switch, and this positive terminal to the positive terminal of this switch, and ground for ground this terminal. This positive terminal of this switch must be connected with the ground, whereas this negative terminal will be connected with the ground. Well, and now I need to simulate. So before that, I must go for simulation command. And what should be my observation window? Here I am going to apply the trigger pulse at 10 millisecond, whereas the quasi-stable state will be of 2 millisecond, for which I have designed my device. So that's why as a whole I am going to consider a 15 millisecond window for my observation, starting from 0 and minimum time step 0.1 millisecond. Okay. Well, now let's run. Okay. Switch, yes. This is another one that, because I have used two switches, so I must these are the generic switches I have used, so I need to include their models. So the model can be included through this spice directory .op. So I need to write .model SW. SW is the name of these two switches, generic name of these two switches, and their model is nothing but the same name, SW, followed by this parenthesis. Well, so this is my 15 millisecond window, observation window, and now first of all I'm going to observe the pulse. Look at it, the pulse is exactly appearing at 10 millisecond, basically 10.01 millisecond, for which I have designed. And if I zoom it, you can see 10.01 millisecond it's appearing, and it's coming back at the 10.02 millisecond. So it's working fine. Well, so next, let's see how these triggers are working. So this one, look at here. Initially, the trigger was connected with the VCC due to this switch. When the triggering voltage was at minus 8 volt, this switch establishes the connection between this VCC and the trigger terminal. So that's why the trigger voltage that I have plotted over here, that is of 8 volt. Now, if I zoom it again at this point, and as you can see, the moment when you have applied the trigger, that means the trigger pulse that switches from this minus 8 volt to the plus 8 volt, this switch gets activated, turning off this switch, because the plus 8 volt turned off this switch and it turns on this switch S1. As a result, the trigger terminal is getting the potential of 0 volt. So that means we can expect, this is a very short negative pulse, so we can approximately assume that it's a negative edge triggered signal. So now I'm going to get this output. Let's see. Look at here. Look at here. This output is coming off exactly 2 millisecond, because at the 10 millisecond the trigger gets applied, and the quasi-stable state, the duration over which the output remains high, is for 12 milliseconds. So basically 2 millisecond window I am getting. And now let's see what will be the capacitor. Not this capacitor, this capacitor. Yeah, the same waveform that you have seen in the in animation, the same type of waveform you are having for this capacitor also. Okay, now let's see whether the whether this potential where the capacitor is capacitor and the output voltage is switching back to zero state is the two-third of the VCC. So let's see. For that, I'm just zooming it in, and this is a marker. I'm setting it at this particular point. Okay, where you can see the vertical values, which is a voltage 5.33. So 8 volt is our supply, two-third of the VCC, 16 by 3. And what is 16 by 3? 16 by 3 is nothing but 5.33 volt. As you can see, the transition is taking place exactly at the two-third of the VCC. And that is the operation for the monostable case. But one more thing, these switches that I have used, there's a problem with this type of switches. You need a negative voltage to turn on this switch continuously, because in order to connect this VCC with the trigger terminal. As a result, this switch consumes some amount of power continuously due to this negative voltage. Although the current which flows from the VCC to the trigger terminal through the switch, that consumes a power, but that is of our interest. That is not a loss. Although some dissipation loss exists over there, but we need these things, so that we will not consider as a loss. But this is a pure loss, because first of all, we do not have any negative potential in our circuit. We only have two rails, +8 and ground. Out of that, I need to apply a negative voltage equivalent to the plus VCC in order to turn on this switch continuously, and that introduces additional power loss. So we can avoid these things. We can avoid this by using real transistors. We can exploit the idea of switching for the NPN and PNP transistors. So first of all, if I consider one is NPN, then if I go for the PNP, now in order to apply the PNP and NPN transistor, I need to switch it 0 volt, 0 volt and 0 volt. And right now, I do not need this -8 volt to turn on the PNP transistor, because the PNP transistor can be turned on for the 0 volt. So that's why we should use real devices instead of using such kind of switches. So initially, this pulse stays at the 0 voltage, and that turns on this transistor, establishing a path between this VCC and this trigger terminal. And when it goes to this +8 volt, then it connects this trigger terminal with the ground. Or for that, I do not need to use this such kind of ground. Rather, I have a ground in my device. Okay, so when this voltage is 0, this PNP transistor is turned on, VCC is connected with the trigger, and this NPN transistor is turned off. When this voltage rises up to the 8 volt, this PNP transistor is turned off, NPN transistor will be turned on, and it will connect this ground to this trigger terminal. Now let's see. So first I'm going to run this one, and first I'm going to check the switching signal. Look at it. The switching signal is appearing exactly at 10 millisecond, 10.01 millisecond, and it's switching from 0 to 8 volt. Now let's see what is the trigger voltage it's getting. The trigger voltage is appearing from 8 to 0 volt exactly at the same position. Exactly at the same position. So it's fine to have a very good trigger. Okay. So obviously our circuit should work. Now going to get the output. Look at here. Okay, zoom it out. Look at here. The output is appearing of 12 millisecond window. That for that I have designed my monostable multivibrator. Well, and let's check the output across this capacitor. Look at here. Now, if you are interested to check whether this potential is coming exactly as 2/3 of the VCC, as I have shown you for the switch for the two generic switches, here also you can check it. 5.33 volt. Look at here over. So this is the operation of monostable multivibrator, using which you can design your home security system, means smoke detector, anti-theft alarm. You just need to apply a sensor to this trigger terminal and a buzzer to this output terminal, and that's all. So if you find this tutorial is helpful for you, please leave comments, share, like and subscribe my channel, and please tell me through the comment box on which topic you are interested that I can make the videos for you. Till then, thank you.